Once again, I'll send around a sign-in sheet. This is the equation of the line we ended up with at the end of class on Monday. This is in slope-intercept form. But there are other versions of the equation of a line. We got this by taking the equation y equals mx plus b. We knew that to start with. But we can also use our slope equation. And if we start with this equation, we can write this like that. If I do a little bit of rearranging, and instead of saying I know both points, I can start with one point being any point on the line. Remember, we had this idea that we were trying to relate any point x, y on the line to our known points, P and Q, wherever they are. I could take that and sub it in for one of these. And if I multiply that x minus x1 over to the other side, I get a different version of the equation for a line that instead of having slope and intercept, has slope and then any point we want to use on our line. This is called the point slope form. And rather than solving for b by plugging in the x and y, I can solve for b by isolating y here. I'll end up with the same equation. The slope-intercept version of the line is unique. There's only one slope-intercept version. There are many different point slope versions, all referring to the same line. Sometimes we prefer to have variables on one side, numbers on the other. So the other thing we can do is we can take this equation, rearrange it to put all of the variables on the same side. I'm not thrilled with that. It would be nicer if they were whole numbers. Multiply through by 4. Actually, I'm going to multiply through by minus 4. Multiply everything in this equation by negative 4 to get an equation written like this is referred to as the general form of a line. Or the general linear form. Usually, writing general linear form is the way we write them when we want to try and solve simultaneous equations, two equations at the same time, find out where our lines cross sort of deal. That tends to be easier for that. Questions? %99 of the time, I'm going to want to write a line in slope-intercept form simply because it's unique, and then I can look very quickly and know whether I got it right or wrong. But that's me. Just talking about this general linear form to use with two lines. If I've got two lines, they could cross. How many times can two lines cross? You sure about that? Say it again. Aha. If they cross more than once, then they cross in at least two places, right? And 2 points determine a line. So if they cross in those two places, they cross everywhere. They're actually the same line. So they could cross once, they could cross infinitely often, or they could not cross 0 times. Lines that don't cross on a flat surface are called parallel. How can I tell from the equations? Why is that going to make them parallel? You're exactly on the right track. The rise and the run have to be the same. Every time I move over and up, I have to keep that same distance between them to keep parallel, to stay from crossing. If at some point they're even slightly different, then as I go out, they're eventually going to cross. Maybe I go out to the right, maybe I go out to the left, but if the distance gets smaller or bigger, somewhere there's crossing. So they have to have the same slope. If my lines intersect, then I can start looking at the angle at which they intersect. And that could be any angle. Ideally, I can use some facts about the slope, a bunch of other stuff I know from physics about vectors and things, to figure out the angle between two lines. But it turns out there's a really easy one if my lines cross at exactly 90 degrees. I'm going to use that a lot. Don't forget radians. So if I create a right angle between my two lines, it turns out then the rise and the run have to exactly reverse each other. This goes back to what I mentioned on Monday about the Egyptian Babylonian idea of slope, where instead of measuring the slope of the actual line by saying I'm going in this direction, I mount something to it, say I'm going exactly away from this. Well, in that case, my two slopes, when multiplied together, give me -1. Quite often you'll see this written this way, which means if M1's a fraction, I take 1 over, that means I flip it. It's a name for flipping a fraction over. Reciprocals. So my slopes are negative reciprocals. But I can investigate that just by looking at slope. Finding the angle in a more general case requires me to do some more weird stuff. We'll save that for later. Questions? Okay. Linear equations are the easiest equations we can deal with. Everything's to the first power. What happens when I start raising those powers? Sometimes. It depends on what's raised second, right? I'm pretty sure what you're thinking of is an equation that looks like this. Or maybe something like that, right? Yeah, that's going to give me a parabola. I get different slopes at different points. But I cannot just look at what happens when I change the power on x, and also look at what happens when I change the power on y. I could change them both. I'll write an implicit equation. Instead of writing that equation y equals, I've mushed up all the x's and y's together on the same side, like the general version of a line. That's not explicit, y is stuff. That's implicit. Wait a minute. This reminds me of something that we did on Monday. Pythagoras. I'm going to take the square root of this equation. This expression right here. We used that on Monday. We used Pythagoras to come up with an expression that looks like this. You're dealing with 2 points. It's the very first question I asked once I graphed those 2 points. Somebody go back to Monday's notes. Tell me what the hell I was talking about. Distance. The distance between 2 points. I don't have one x and y up there. That's a distance setup. That's telling me the distance between my point x, y, and the point 0, 0 is 5. I want the set of points that make this equation true. That's the graph of an equation. It's the set of points where all of those things obey this rule. Here's the point 0, 0. I want the points x, y, whose distance from this point is 5. What shape have I just made? Say it again. A circle. As a matter of fact, we usually write that without the square root in it. I've got a circle whose center is at 0, 0, and whose radius is 5. Go out 5 units in any direction you want from my point 0, 0, you're going to get a circle. I can do this from any point. I don't have to be at 0, 0, right? I could write this x minus h squared plus y minus k squared equals r squared. And I have a circle whose center is at hk. And whose radius is r. This equation right here, based on our distance formula, this is the standard form for a circle. I claim that's also a circle. How do you know I'm not just talking? If that's a circle, I should be able to make this equation look like this one. Factor how? I'm sorry? Okay, so let's do some grouping. X squared and 2x get grouped together. Y squared and minus 6y get grouped together. I'll throw this 7 on the other side for the moment, and we'll deal with that later. There's a procedure I'm doing here that should maybe tickle your fancy. I think weirdest sense of deja vu. I've seen this crap before. What am I doing? What's this thing called? completing the square. Why is it called that? I'm not actually completing a square root. Remember I said earlier that algebra is a shortcut for geometry? Al-Yabar et al-Muqabala, the method of completion and reduction. I'm completing. I'm actually doing geometry. You're going to say something. Am I wrong? Yeah. I've got two more x's I need to add to this, right? So let's make a little rectangle. That height will be x, that width will be 1. I'll make another one up here. Oh, yes, absolutely. Notice I've got something that this particular image is 2,800 years old, called a gnomon, Gnomon. That gnomon is missing its upper right corner. What goes in that upper right corner? A little bitty square of size. What's its length? What's its height? 1 by 1. Which means its area is 1. Which means if I add 1 here, I will have completed a square whose side has length x plus 1. Completion and reduction. There's my square root part. At some point, I'll reduce my equation, right? But I have to balance this. If I put a 1 on the left side, I have to put that same one on the right side. Please notice, in order to make this square the right size, I have to take this middle term and divide it into two pieces. So now let's move to the y's. Do the same damn thing. I didn't even need to draw the picture. I'm going to take this 6, divide it into two equal pieces. Each one will be 3. So instead of where I have a 1 here, I'll have a 3. What's going to be that little square I add? That little tiny little top right corner to complete my gnomon will have what size? But it'll be 3 in length and 3 in height, so it'll be 3 squared. I add a 9. If I add it on this side, I have to add it on this side. And then this is y minus 3 squared. And over here, I get 3. It's a cycle. That's the right form. Almost. Because when I wrote the original equation, root x minus h, y minus k. I got a plus here. How do I fix that? I really want it to be a minus. Because that was our distance idea, right? Change in x, change in y. I should have a minus. I can write it as x minus negative 1. So now I know the center. The center of this circle is negative 1, 3. That's the h and the k. And the radius? This is r squared. So the radius square root of 3. It worked. I wish I was making this up. I had a cuneiform version that has this picture on it, written in Babylon almost 3,000 years ago. This isn't new stuff, people. Been doing this forever. I can do all sorts of different things with my second degree equations.
Why is -7 plus 5? Oh, no.
1 and 9, yes. I added the 3 squared. I guarantee you, the most common mistakes at this point in the game are sign errors and arithmetic errors. Every time I make them, I've been making them for 40 years, and I'm not going to stop anytime soon. We'll all catch it. We'll all fix it. Don't worry. Happens regularly.
What happens to the other 7 if it's constant numbers?
You mean here? Because I want to balance the equation. I added it to the left. That would make the left heavier, right? So I need to add it to the right to even that out. If I kept it on the same side with the left, I could subtract it, right? I have a +1 and a -1, have a +9 and a -9, but then I take the parts of them over here, they change sign. More questions?
Exactly, derive shape the box.
Oh, I said I've got a square here, right? And I'm going to take the middle and split it to pieces.
So each term represents square.
Well, what actually happened is the x squared piece, that's this.
Yes.
And then I split this in half to be 1x up here and 1x down here. Because I want it to look like a square with a corner missing. A square I have to complete, thus completing the square. That, again, that's the trick I'm stealing from Babylon. Over here, if I'd done it in Y's, when I did this side, would have been y, y, 3y, 3, 3. So this piece is 3y, this piece is 3y, this is y squared. And then my upper little corner to complete the square is a 9. What if I take square, if I take a circle, grab the sides and stretch? I get an oval, right? Mathematically, because it's symmetric, we call it an ellipse. I'm a crap artist, so we'll just run with this for the moment. I'm going to have a different horizontal distance than I am vertical distance. I'm going to start this at the center. We'll move it anywhere in a moment, but I'm going to start with the same distance idea from the center. Let's call this distance A and this distance B. So I have a major, the long one, and a minor, the small one. That means I don't have a constant radius like I did up in the circle, yes? Let me take this circle equation for a second. I'm going to mess with this equation. I'm going to take the right-hand side, make that a 1. So I'm going to divide everything by 3. And I can think of those 3's that are currently in the denominator for my circle as telling me how far I go in the x direction and how far I go in the y direction. Those are my radii. The radius horizontally, the radius vertically. It's a circle. They're the same number, right? If I make them different, I can change the way that shape looks. To adjust a circle into an ellipse means to make these two numbers different. That's it. The equation for an ellipse looks just like the equation for a circle, written this way, with different numbers on the bottom. And the bigger number tells me which direction is bigger. If A is bigger than B, then this is an ellipse whose major axis is horizontal, because the X has the number that's bigger under it. If I switch them, then it's going to go this way. So this one goes vertically. And again, this one's tight. Those are my A and B. I will tell you, though, that I'm fairly bad at drawing ellipses. And I used to do more woodworking than I do now. When I did woodworking, wanted to make an oval table. And so I asked myself, how could I make an oval table easily? I went to a woodworking store out in Robinson, and they had an oval cutting jig for $100. And I said, F that, I'll do some math. Every ellipse has two more important points here. Just like we have the center for a circle, we have a center for our ellipse, but then we stretched, right? Think of stretching as tearing that center into two other points, which are partway out. Those 2 points are called the foci. That's the plural of the word focus. And it turns out that there's a very nice property for every ellipse. If you take any point on the ellipse and you measure the distance from the foci to that point and add those two distances together, you get the same number every time. That number happens to be the major diameter of the oval. So if I measure from this point out to any spot on the ellipse, and then I measure from that spot back to the other focus, and I add those two together, that total's constant everywhere on this shape. So all I need to know is how wide I want to make my oval. And then I need a string that's that long. I need to know where to put 2 nails in the wood, stretch it out, and draw my oval. My oval cutting jig costs a nickel. It's 2 nails and a piece of string. But in order to find these, depending on whether I'm having that be a y coordinate or x coordinate, so it'll either be up or down by c, left or right by c, it turns out it's almost Pythagoras. All I have to do is measure the numbers I already know. If I know how wide I want it, and I know how wide across I want it, the length and the width of my oval, I know exactly where to put those 2 nails. Questions? Yes, ma'am.
So, you was larger than, what you would probably on the square.
Well, we're always going to call the bigger number A in this case. So I'm never going to have B be bigger than A in this situation. But yes, I would just reverse all the letters. But I'm just saying, okay, whichever number is bigger, that's A. That's just going to make my life easier here. It turns out that this idea of measuring the distances between 2 points, that's really the same idea as what we were measuring the distance of 1 point. That was how we got our circle in the first place. Now we just added another point. So geometry really culminated in ancient Greece about 300, 200 BC. What if I didn't add the distances? What if I subtracted them? Then my distances could keep getting bigger, right? Since I'm taking something off. I could have the distance to one focus be really huge, and then the distance to the other focus be even bigger. My points would get further away. So instead of being contained, my shape is uncontained. And it goes out to infinity. A hyperbola. Take your ellipse and rip it inside out. Where's A? Where's B? Well, I'm going to use the same idea for A again. A is going to be the distance to where we cross the axis. We'll call that a vertex. But B should go the other way, right? I'm an absolute crap artist, so we're going to imagine that those go through the corners of this box. This is the point B. On our ellipse, the ellipse was inside the box. Go back and look at this picture again, up here. If I drew a vertical at B and a horizontal at A, I'd get that same box, but the ellipse would be inside it. So really all I've done is take it and turn it inside out. But now, I don't care which one's bigger. I care which one's got the plus sign and which one's got the minus sign. Because X has the positive sign, we're going in the X direction. If I had this equation, that one would be going vertically. Oh, that's a horrible looking piece. Question for you. What's the slope of this line? Again, assuming it actually goes through this corner. Wait a minute. That corner is over A, up B. Our rise is B, our run is A. Because we started at 0. And down here, that's just going to be the opposite corner, so that'll be negative B over A, X. So if B is larger than A, these are going to be steep lines, and we'll have a really wide hyperbola. And if A is bigger than B, we'll have narrower, skinnier hyperbola. reverse those letters for this case. Trig covered these. So some of this, you're being, I think I remember this stuff. Maybe long time ago in a galaxy far, far away. I don't expect you to memorize this crap this early, but we're going to use these shapes frequently. We're going to need at least a reference. When I look at this equation, I should know what it is. There are two different versions of a formula sheet on our Canvas page. So you have access to it, but you don't get formula sheets for an exam like that. If you hit the apps button on your graphing calculator, there's a whole bunch of stuff already built in here. Take a look at number 4. All of these equations are in here, along with the shapes that go with it. Hey, look, a squared under the x term. That ellipse is located horizontally. A squared under the y term, that one goes vertically. Hyperbola. Horizontal versus vertical orientation, same thing. Which one's positive? Is x positive? Then we're going side to side. Is y positive? We're going up and down. There's one other shape I didn't talk about, and that's the parabola that started our comment. Parabola only has one square. But as we said earlier, it could be the x that is squared, in which case we're either going up or down, or it could be the y that is squared, in which case we're going left or right. It's like one part of the hyperbola. This number p is the distance for the focus. Parabola only has one focus because it's only got one piece to go around. That distance right there, that's the focal length, like in a camera lens. Longer focal length, you get further out. Shorter focal length, you get wide, the same thing. Please notice, we're going to do a lot of completing the square to get these to look like our standard form. There's a Word document version. There's a PDF version. You should play with these. Questions? I already mentioned it once. Let's talk trig. I am 100% evil on trig. Degrees suck. I want you to take your calculator. I want you to hit the mode button. On that third line, highlight radian, hit enter. Never change it. But I'm in chemistry, I'm in physics, I need degrees there. Yes. So, when you're in chemistry and when you're in physics, down here above that apps button, what does it say right above apps? Angle. If you need an angle in degrees, you hit, and there's the degree mark. You want to work in degrees? You don't take your calculator out of radians, you stay in radians, and you use the degree mark. I cannot tell you how many AP people I have saved their asses on when they switch from the calculus exam to the physics exam, or the other way around more often, and they have their degrees set up, and they do all the calculus stuff wrong because they're in degrees. Okay, so it's under the apps button here. You hit second angle, and it's that very first option. By the way, that third one is the R mark. They used it for radians, but radians don't actually have a unit. So I don't know why they made that up. The little tick mark, That's for subdividing degrees. What's the subdivision of a degree? A fraction of a degree. A small part, minute, minute. Degrees, minutes, and then we divided it again because it's the second subdivision. By the way, that's the reason it's that way on the clock. Minutes and seconds because it's a small part, and then the second small part. Etymology is fun, really. DMS, degrees, minutes, seconds. We're going to stay in radians. Radians are much more useful in general. I know degrees are intuitive, but they were made up. Do you know why there are 360 degrees in a circle? Do you know why 90 degrees is a right angle? It's a right angle because it's the right one to use so your building won't fall down. There are 360 degrees in a circle because 360 is divisible by a lot of stuff. It's a very composite number. It's not prime. It's got a lot of factors. And Babylonian and Egyptian mathematicians always like to write their fractions 1 over something. So you needed a half, a third, a quarter, a fifth, a sixth, an eighth, a 12th. You could do all of those with 360. You can divide it by a lot of stuff. That's it. They made it up. So instead, we'll make up something else. If I have a circle whose radius is r, then what is the circumference of that circle? That's the area. Aha. So an angle actually measures the fraction of the arc cut out by that angle. So I'm going to take this length, call it S, the arc length, and I'm going to measure that. And I'm going to define my angle to be the ratio of those two. That's it. That's the definition of an angle. Please notice, if I'm measuring in feet, both of those are in feet. If I'm measuring in centimeters, both of those are in centimeters. If I'm measuring kilometers, these are both in kilometers. That means that angle doesn't have a unit. And that's why radians don't have a unit or a mark. But now I say to myself, wait a minute, if I go all the way around the circle, that's 360 degrees. If I go all the way around the circle, that's the circumference. What happens? Oh, the r's cancel. Once around the circle is 2 pi radians, or 180 degrees is 1 pi radian. Which means if I want to convert from one to the other, I multiply by a fraction. If I'm going 2 radians, that fraction is pi over 180. If I'm going 2 degrees, it's 180 over pi. So if I tell you I've got an angle of 45 degrees, but I want it in radians, I take this ratio. Pi radians, 180 degrees, the units will cancel. This is pi over something. 45 over 180. Say again? It's 0.25 if you do division on your calculator, so that's a fourth. Pi over 4. We're going to use 5 angles most often. So I should know these in radians. I should know them cold in radians. And those are, well, we already did 45 degrees. That's pi over 4. 0 is just going to be 0. What about the rest of them? Because it's half of 180, right? 180 would be a whole pi. So pi over 2 is 90 degrees. I should be able to take those angles and move them to the other quadrants. So let's picture this flipped over. If I'm in the second quadrant, I should be able to get the mirror images of these three. Oh, wait a minute. If I flip this over, I'll be at 180 degrees, right? If I flip this over, where will I be? 150. I'll be 30 back. Wait a minute. Let's do it in radians. If I flip this over, I'll be at pi. I'll be pi over 6 back. That's 5/6. A whole pi take away 1/6. If I flip over to here, 180 minus 45 is 135. But that's also a whole pi minus a quarter pi. So that's 3/4. If I flip this over, 180 minus 60 is 120. 120, well, a whole pi minus a third of a pi is 2/3. I should be able to do the same thing down here in quadrant 3 and down here in quadrant 4 and fill out all of these angles in radians on my unit circle. If you need one, we've got lots of blank drawings of the unit circle over in the enrichment center. And you can practice filling them in over and over and over again. Nauseatingly tedious. But at some point, those numbers and the next set of numbers that go with those angles have to come vomiting out of your head like song lyrics. So we used our unit circle to define the trig functions. Believe it or not, here is another case where the fact that the rest of the world doesn't speak English effed us up. The reason we call it the sine function is because it was named in Arabic as the fold. Fold. Well, you've seen the graph of the sine. What's the graph of sine look like? It looks like a bunch of stuff folded up. When you write in Arabic, you write consonants only. You don't write the vowels. The vowels are diacritical marks, little marks below or little marks above. So when you write in Arabic, you don't write vowels. So they wrote fold, jaib. No, jiba. When it got translated back to Latin, it got translated as jaiv, which means cavity, pocket, a fold in a piece of cloth where you put the fold. Makes sense, right? What's Latin for cavity? Here's a hint. There are some in your head. Sinus. And so we called it the sinus function. So the reason we call it sine theta is because we don't know how to read Arabic. Cosine, the complements sine. Secant, cosecant, tangent, cotangent. We were given them all in terms of the circle. We were given them all in terms of triangles as well. I find the circle definitions to be a little more useful. There are a table of values, again, that you should know for sine and cosine. Where did I put my table of values? I apparently ate my table of values. Here it is. I hate memorizing this damn thing. I'm going to teach you my favorite cheat. I need you to hold up your hand. thumb up, pinky to side. 5 lines, 5 angles. 0, 1, 2, 3, 4. If I'm counting up, I'm doing the sine. If I'm counting down, 0, 1, 2, 3, 4, I'm doing the cosine. Take whatever finger you land on, take that number. Take its square root and divide by 2. You want to go up or down? Sine or cosine? Pick one. Sine, I'm going to go up. 0 divided by 2 is 0. 1 divided by 2. 2, take the square root. Square root of 2 divided by 2. Square root of 3 divided by 2. What's square root of 4? 2 divided by 2 is 1. Sine goes up, cosine goes down. Tangent is sine over cosine. If I know sine and cosine, I know the rest of those. Secant is 1 over cosine. So there's a bunch of identities. Remember all of this garbage? All of Appendix D is full of this list of identities. There will be some we use. I don't want you to go through and memorize this crap. The ones we use will be the ones you end up remembering. I am going to recommend that you work through those problems that are listed for our homework for appendices A, B, C, and D. You don't have to turn those in. The keys are already on our Canvas page. That way you know what I'm looking for in terms of explanations of handed in problems, and you get a chance to review this stuff. And if it doesn't look familiar, you should come talk to me now. Within the next day. Friday, we're going to start calculus. Well, what do we do before then? We have class tomorrow, right? 12:45 to 2, right here. See you then.